live. All right. Welcome everyone to the spring semester of the Living Earth Collaborative seminar. We hope you all had a wonderful break and were able to stay safe, you and your family. And yeah, we're excited to get started. So just a reminder, at the beginning of these seminars, we'll have slides from the Biology Inclusion Committee, which you're seeing now. And then we will jump into our talk. All right, so as Dr. McGinley loads up his slides, I will give the introduction. So today we have a wonderful scientist starting us off strong for this semester, and that is Dr. Rowan McGinley. He comes to us from St. Louis University, where he's currently a postdoc. Dr. Rowan McGinley is not only an excellent researcher, but he's also a fantastic natural historian, incredibly knowledgeable when it comes to arachnids and insects. And he's had a long training in both spiders and insects. Before joining Dr. Casey Fowler Finn's lab at St. Louis University, he was a postdoc fellow with Eileen Hebetz at the University of Nebraska in Lincoln. And before he went on to get a postdoc experience, he did his PhD with Phil Taylor at Macquarie University in Australia. I don't want to give away too much, but his general interests are mate choice, the ecology and evolution of arachnids and insects, along with sensory biology. I've seen parts of his talk today, and I'm really excited to see the videos. So I can guarantee you this is going to be a very fun and exciting talk. Dr. McGinley, please take it away.
Thanks for the intro, Brett, and thanks everyone for tuning in. So today I'm going to talk about my PhD research, which I did at Macquarie University in Sydney, Australia. So it was all about jumping spider contests. So here's just an outline of what I'm going to be talking about. So first, I'll start off with the kind of more boring stuff, the theory and predictions behind animal contests, and then we'll get into the exciting stuff about the jumping spiders, looking at why they fight, who wins the fights or wins the contests, why they might win, and how losers decide to withdraw from contests. So animal contests, so what are they? So they're direct and discrete behavioral interactions that determine the ownership of indivisible resource units. So animals engage in contests in order to obtain resources. So it's a form of competition, but it's not quite like scramble competition. And it doesn't always necessarily involve physical fighting. So for example, butterflies aren't very good at attacking each other, injuring each other, but they can still engage in contests. So they can engage in these flights, so they display in order to determine the ownership of sunny spots in the forest, for example. So animal contests are a widespread phenomenon, as you can see in these examples on the right. And animals communicate and attack each other during contests. So contests can drive the evolution of animal signals as well as extreme weaponry. But contests can be very costly, and these costs might include things like time, energy, risk of being injured, and in some cases, even the risk of death. But if you watch a lot of contests, you might notice that animals are often able to settle contests, decide who gets the resources without escalating to injurious fighting. And so what a lot of researchers that study animal contests ask is how animals manage to limit these costs while still determining who gets to keep the resource. So one solution to this problem is for animals to decide which opponent is going to would win a fight without actually fighting. And so they might be able to do this by exchanging information about their relative fighting ability. So under this scenario, contest is expected to end when the weaker rival determines that it's weaker and then it withdraws, and then the contest ends. And so this is generally referred to as mutual assessment. So the animals are thought to be mutually assessing each other. And one disadvantage of this approach could be that the exchange of information could itself be costly or difficult. And under this scenario, so mutual assessment is easier to do when there are large differences in the relative abilities of the opponents. So if there's a big difference between them, then it's easier to determine which opponent's better. And conversely, when they're closely matched, contests are expected to be more escalated, involve more costs. And so an example of a theoretical model that outlines how such a strategy could work is this sequential assessment model. Under mutual assessment, because they're assessing each other, we expect to find this negative relationship between the difference in the fighting ability and the costs involved in the contest. So when there's a large difference between the opponents, expect the contest to be resolved pretty easily. And when there's a small difference between the opponents, expect that that's when the costs and escalation are going to increase. But there is another potential solution to the challenge of reducing cost in contests. And this solution is generally referred to as self-assessment strategies or own resource holding potential persistence. And so basically under this strategy, you limit costs by just persisting up until the cost threshold. And once you reach your threshold, then you withdraw from the contest. So better fighters are those that have higher thresholds. And in any given contest, the individual with a higher threshold is going to end up being the winner. And whoever reaches the threshold first becomes the loser. A disadvantage of this strategy is that losers will always persist up until their threshold, regardless of the quality of the opponent. And some theoretical models that outline how this strategy works include the wars of attrition. And so under a self-assessment strategy, we expect to find this positive relationship between the finding ability of the loser or the weaker rival and the cost involved in the contest. So when the loser has a higher threshold, that's when the costs are going to be higher. Okay, so we have these predictions for mutual assessment, this negative relationship between difference in finding ability versus costs, and for self-assessment, this positive relationship between the loser or weaker rival's finding ability and the cost involved in the contest. But there is an issue here, and that is that differences are determined by the quality of the winner as well as the quality of the loser. So the loser's quality is not an independent measure, independent of the difference. So what does this mean? So you get large differences by having, the largest differences occur when you've got really small or really weak individuals versus the largest or strongest individuals. And so what this means is that at this end of the size spectrum, you can expect to get low costs, either because the individuals have lower thresholds because they're smaller, or because there are larger differences because the smaller the one rival is, the bigger the difference is going to be. And at the other end, you expect the opposite. So you get high costs, either because of high cost thresholds or because there are smaller differences. So it's hard to tell whether they're using self-assessment or mutual assessment. So all that is just to say that you expect this negative relationship between the difference in finding ability versus the cost for both mutual assessment and self-assessment. However, this wasn't really recognized formally until 2003 when this paper came out, outlining this statistical issue. And so a lot of studies done prior to this use this relationship as evidence of animals using mutual assessment, even though it didn't exclude the potential use of self-assessment. So a better way of distinguishing between these strategies is, rather than use the difference, is to look at the absolute quality of each opponent. So for example, if size is a good measure of finding ability, then you look at the larger rival size and the smaller rival size, or the winner's size and the loser's size. And if you do that, then you expect to get low cost when the larger rival is very big and when the smaller rival is very small, if they're using mutual assessment. And for a self-assessment strategy, again, you expect this same relationship between the smaller rival size versus cost as we had previously. But we also expect to not really find a relationship or an effect of the larger rival size, except that you do get this slightly negative relationship because they have to be bigger than the other rival. And another way to distinguish between these two strategies is, rather than having randomly matched opponents, to stage contests where opponents are size matched or matched for finding ability. And so if they're matched for finding ability, then we should in effect expect that there is an effect of size or finding ability on the cost. So if you have a pair of large individuals or a pair of small individuals, the difference between them is still going to be the same, so costs aren't going to change. But if they're using self-assessment, then they will have different thresholds based on their quality. So larger pairs or better fighters, even though they're matched, will still be expected to escalate to higher levels and incur higher costs. Okay, So here's just an empirical example of what all of this means. So back in 1999, there was a study published on stalk-eyed flies where they looked at contests in these flies and they examined the size difference between opponents and the cost involved in the contest, and they found this negative relationship. And so the conclusion was that they use a mutual assessment strategy. However, there was a follow-up study done in 2009 where they assessed the larger rival size and smaller rival size independently rather than looking at the difference. And they actually found that it was only really the smaller rival size that matters, not the larger rival size. And so this just illustrates that when you don't, if you only look at the difference, then you might get misleading results. And so since that 2003 paper where all of these issues were outlined, there have been enough studies where people have used more appropriate analyses. So there have been enough to come up with meta-analysis, and this actually shows that animals seem to be using self-assessment more than mutual assessment, which wasn't thought to be the case previously. Okay, so that's enough about the theory and predictions. So now I'm going to get into talking about jumping spiders. So I'm going to try and cover 4 different questions during the rest of the talk. So first we'll start off just talking about jumping spiders. So they belong to the family Salticidae, which is the largest family of spiders, and with more than 6,000 described species. They differ from many other spiders in that they don't build prey capture webs, at least most jumping spiders don't. They're also different from most other spiders in that they have very well developed vision. And along with that, they're also known for their elaborate visual displays. So there's some peacock spiders here showing off their bright colors and displays. But a lot of other spiders also use visual displays as well. The species I worked with wasn't so colorful. So this is Servaea incana. They are a common jumping spider in southeastern Australia. They inhabit eucalyptus trees, the trunks of eucalyptus trees. So there's a female here on the left and pictures of males on the right. So you can see there is some sexual dimorphism. So the males have these darkened chelicerae, these darkened mouth parts and forelegs. And they use these during displays, both during contests and during courtship. So there's not much in the way of sexual size dimorphism, but there is a difference in the size range of males and females. So the largest males are about twice the size of the smallest males in terms of linear measurements, which equates to about a 5 times difference in mass between the smallest and largest males. But average and median size of males and females is about the same. Okay, so first question, why do they fight? So we did a couple of studies, Vivian Mendez and I. She was another PhD student in the lab at the time. So one of these studies was looking at remating inhibition, and we found that unmated females are very receptive to mating. So they'll mate with pretty much the first male that they encounter. But after they've mated once, they're very unlikely to mate again. And we also conducted a phenology study where we went out into the field and conducted population censuses. And we found that males mature early in the season than females. And so it seems that adult males seek out and guard penultimate females. So this is an image of a tree trunk with a female, an immature female in her retreat and an adult male here. So when this female matures, when she goes through her next molt, she'll be sexually mature, and if this male is still around, he'll be the one that gets to mate with her. And so it seems that males engage in contests, so they mature before the females, and then they hang out and engage in contests with each other in order to gain access to unmated females. And so this is a video illustrating what happens when 2 males meet at a female's retreat. these videos, just in case anybody was expecting sound. So why do they fight? It's in order to gain access to receptive females. So who wins the fights? So I staged this experiment where basically I just got pairs of spiders, male Servaea incana, put pairs in an arena and filmed them and measured their size. And then check which spider won. And so we found that size, so here measured as cephalothorax width difference, so basically the width of the head, is a very good predictor of contest outcome. So when there's a large difference between spiders, the larger spider is very likely to win, and the smaller spider is very unlikely to win. And when they're about evenly matched, about the same size, it's about 50% chance that one spider or the other is going to win. So size predicts outcome. So who wins? Large males. So the next question is, why do winners win? So why do the larger spiders win? So to address this, we conducted this study of whole organism performance. So basically we got 20-something males, and we put them through a series of physical tests. So the 4 trials were vertical running speed. So we chased them up this wooden tower, timed how long it took them to reach the top. We did a similar thing along a horizontal racetrack. We also examined their endurance capacity by chasing them around in circles until they collapsed. And we also measured their pulling force. So we hooked them up to this fishing line, which went over a metal rod that was attached to a little bucket, a little container, and we add water to that until the spider was pulled off, so we could measure their performance. And that's what those trials look like. And so we examined their performance in relation to their body size, but also their relative leg length and relative mass. And so what we found was that body size predicts performance in a number of these trials. So larger spiders were faster at climbing, and also spiders that were heavy for their size were faster at climbing. We also found that larger spiders had higher horizontal running speed. We didn't find an effect of size on endurance capacity, but we did find that relatively heavy spiders had higher endurance. And we also found that size predicted pulling force as well. So larger spiders were able to withstand greater forces before being pulled off this rod, as well as spiders with long legs for their size. Okay, so why do winners win? It's probably because they're faster, bigger, and stronger than smaller spiders. Okay, so how do losers decide when to give up? So this is getting back to looking at the assessment strategies that I was talking about at the beginning. So these are the predictions that we have if they're using mutual assessment versus self-assessment. So here they're deciding to give up based on the relative abilities of the opponents. And here they're giving up just based on some sort of cost threshold, rather than their opponent's ability. So in order to determine which strategy they're using, we need a measure of fighting ability as well as a measure of cost in these contests. And so we already have our measure of fighting ability that I mentioned before. So size is a strong predictor of outcome. So we can use that as a proxy for fighting ability. And because size predicts outcome, I also ran an additional 73 contest where spiders were size matched as well. So we can test that other prediction that we mentioned earlier. And then in terms of contest costs, one way that we looked at costs was looking at the level of escalation involved in these contests. And so we defined 6 levels of escalation, and any given contest could end at any level, any of these 6 levels. So the lowest level of escalation was just mutual orientation. So the contest always started when both spiders turned to face each other. And sometimes that was enough that one spider would turn and flee. But usually they would escalate to the next phase, which we call the hunch. So this is basically when the spiders start to display, so they both, or one or both of them will lift their body up off the substrate, they'll tuck their abdomen underneath, and they'll also raise their first pair of legs. If that's not enough to deter one of the opponents, then they'll escalate to this approach phase. So one or both spiders will start to approach the other. And then if one spider still hasn't run away, then they'll escalate to sparring. So this is when they first start to make physical contact. The spiders will lunge towards each other and they'll push against each other's legs. And then if that's not enough to resolve the contest, then they may escalate to embracing, which we saw in the first video that I showed. So they'll lock their mouth parts, and they'll push and pull against each other on the substrate while they have their forelegs out to the side. And then in very rare cases, they'll escalate to struggling. So basically at this point, they're just rolling around on the substrate, grasping, biting at each other. And so this figure is just showing the number of contests that involved each of these levels of escalation. So all contests involved orienting, but very few involved struggling. And these first three stages are the pre-contact phase. So this is before the spiders have physically interacted with each other. And then these last three levels of escalation are the contact phase, where they're actually physically interacting. Okay, so then how do the size and the costs relate to each other? So in size unmatched contest, we found that there was an effect of the size of the smaller rival on the probability of escalating from the approach level of escalation to the sparring. So that's from the third to the fourth level, which goes from the pre-contact phase to the contact phase. So we found that the larger the smaller rival is, the more likely they were to escalate to the contact phase. And similarly, when spiders were size matched, we found an effect of size as well. So again, larger spiders were more likely to escalate from the non-contact phase to the contact phase. And so we found that smaller spiders are less likely to escalate, regardless of the size of the opponent. And so this is consistent with self-assessment strategy. So these patterns on the right. Okay, so how do losers decide when to give up? It seems that smaller spiders give up based on escalation, so they're less willing to escalate, and this is regardless of the opponent's size. But then this raises this hidden bonus question of why they don't assess their opponents during these contests. So as I mentioned earlier, these spiders have very good vision and they span a huge, relatively large size range, with the smallest males being half the size of the largest males. So I conducted this more manipulative study rather than just relying on correlations. So I did this video playback experiments. And so what we did here was to film 3 large and 3 small spiders. So spiders will display towards themselves, or jumping spiders will display towards themselves when they see their reflection. So I put the spiders in front of a 2-way mirror with a camera on the other side. And so I was able to record the spiders' displays front on. So I had 3 large spiders and 3 small spiders. I then scaled these videos to 4 different sizes. So the original small and large size, and I scaled them down to a tiny size, so just under the smallest live spider size, and then a giant size where they were bigger than most other spiders. And so then I got some live spiders and got each of them to watch 8 different videos. So each spider watched 4 videos of a spider that was originally small, that was scaled to these 4 different sizes. And then they also watched 4 videos of a spider that was originally large and then scaled to 4 different sizes. So I had 81 spiders, which involved a lot of trials because they had to each go through 8 trials. And spiders went through these trials once every 2 days. And during the trials, I assessed whether or not the spiders displayed towards the video, which was played just on this iPod Touch, and also whether or not they approached within 30 millimeters of the screen. So when they get to within that distance, that's usually when they start to escalate towards the physical interaction. And because they can't really engage with such an interaction with the video, we didn't assess anything beyond that. And then our predictor variables were the size of the live spider, as well as the original size of the spider in the video and the final size of the spider in the video. And this is what these trials look like. So there's an example where the spider didn't display and didn't approach. And an example where he displays and goes right up to the screen. Okay, so we'll start off with the approach results. So we found an effect of both the opponent size, so the final size of the video, as well as the live spider size. And we didn't find an effect of the original spider size, the spider's original size in the video. So in terms of the size of the video opponent, we found that spiders weren't that interested in approaching the smallest size videos, but they were most likely to approach the second smallest size, the small videos. And then as the size of those videos increased, they became less likely to approach them. We also found an effect of the spider's own size. So larger spiders were more likely to approach than smaller spiders. And this was the same across the different size videos. So what this suggests is that spiders are capable of assessing their opponents during contests. So this suggests the capacity for mutual assessment. And then looking at the display results, we also find effects of opponent size and own size. But here we found an interaction. So like with the approach results, we found that all spiders weren't really interested in approaching, displaying towards the tiny opponents. But all spiders were more likely to display towards the smallest size opponents. And then as the video size increased further, we start to get this trend that the larger spiders tended to display more than the smaller spiders. And this became even stronger for the giant size videos. So only the larger spiders, well, the larger spiders are much more likely to display towards the giant size video than smaller spiders. So smaller spiders are unlikely to display towards the largest video. So again, this suggests some capacity for mutual assessment. So of course, this raises the question of why we didn't find support for mutual assessment in the live contest if we found support for it during the video playback experiments. So one potential explanation is that the video playback experiment setup is kind of the ideal situation for assessment to take place. So you've got this video, this stationary opponent just standing there continually displaying, but that's not exactly what happens in the live contests. So if we go back to our display results, from the video playback experiments, we see at the smaller end of the spectrum, the smallest videos are more likely, the smallest spiders are more likely to display towards smaller opponents than the larger opponents. And at the other side of the spectrum, we see the opposite thing happening. So the largest spiders are displaying more towards the largest videos than they are towards the smaller size videos. And so it seems like maybe small spiders aren't displaying towards large spiders and large spiders aren't displaying towards small spiders. And so perhaps these effects reduce the opportunity for assessment during live contests. And so what this might indicate is that there are costs of mutual assessment and that they might be different for small spiders and for large spiders. So for small spiders, maybe sharing information about your small size isn't that helpful because you might be likely to lose anyway. And maybe increase the chance of winning if you don't help the largest spider, the larger opponent, make a good decision, so they make a mistake. At the same time, trying to gather information about your opponent could be risky, because they could be attacked while trying to gather information. And so a better strategy might be to just deter an attack and escape, rather than escalate into an or potentially get involved in a physical interaction, since we know the larger spiders are faster and stronger. So for large spiders, sharing information about your large size might not be that helpful as well, because small spiders might not be a real threat. And there might be potential cost of displaying, which could be greater for large spiders than small spiders, such as energy expenditure, as well as the risk of making yourself conspicuous to predators. And one of the advantages of not sharing information with small opponents is that you won't scare them off. And because spiders can be cannibalistic, this means that large spiders could prey upon the smaller spiders if they're not advertising how much bigger they are. So this is an example where this larger spider, rather than displaying towards a smaller opponent, just waited until it was close enough to pounce and attack it. Okay, so why don't the spiders assess their opponents? For both large and small spiders, it seems that there may be little advantage to exchanging information. And so that brings me to the end. And so I want to thank my advisor, PhD advisor, Phil Taylor and John Prenter, and also Vivian, who was a fellow student at the time. So we both worked on this species together throughout our PhDs. And then I want to thank a bunch of people who helped me along the way at Macquarie University, as well as the Heberts Lab and the Fowler Fin Lab. So I guess we'll open up to questions. Thanks.
Excellent. Thank you, Rowan. I can hear everyone clapping. It's fantastic. Thanks for including such wonderful videos for our first seminar, getting things back up and running. And we do have a couple of questions already coming in, but I want to remind viewers to please post your question in the chat on YouTube Studio. Yeah, so actually we'll start the questions off with one from John Birmingham. He asked, to what extent does psychology play into contests? Can self-assessment be disassociated from fighting ability?
So there are potentially lots of different things that can influence fighting ability. So their prior experience, their motivation, the quality of the resource, which might differ, like the relative quality of the resource for each opponent might differ. Yeah, does that answer the question? I'm not sure.
I think so. I mean, it's tough. I think it's a very good question. I don't know how you would test in a spider though, right? Like to actually figure out what the individual spider thinks their size is, right? Would just maybe show that they're a more bold spider if they're going after big spiders. Is it because they think they're bigger spiders than they are? Or, you know, I don't know how you would actually test that.
Yeah, I guess you'd have to find out the mechanism that links size versus their tendency to escalate, which may vary with their past experience.
So here's a follow-up. Actually, I should include this as well. So this is from John Birmingham. He says, "How does a spider assess its size? Isn't size relative, which would lead to mutual assessment?"
Yeah, but it's a good question that I often get a lot. In general, I guess it's good to know that these spiders are predators and prey, and so it's in general good for them to know their size relative to the world around them. But the mechanisms underneath that aren't really well studied, I guess. A lot of my research during my PhD was trying to figure that out. I was trying to measure biogenic amines in these spiders and see if that varies with size. But it was difficult to do with the spiders. They don't have the best physiology for those kind of experiments. But yeah, we were trying to see if serotonin or dopamine levels predict behavior during contests, or whether it's related to size and yeah, things like that.
Cool, very cool.
Thank you, Rowan, for a wonderful talk. That was really interesting. I'm going to ask a question of my own. So I'm wondering about, I guess, the assessment that the spiders can get from different escalation stages, because before contact, they can only, I guess, assess for size. But once they get into the spurring stage, they could potentially assess for strength. So is it possible that there are, I mean, I'm just wondering the distinction between self-assessment reaching the threshold versus getting enough information to make a decision, kind of like an accumulation of information. And I'm just wondering what's your view on this, and I guess, what kind of pattern would show up in these two alternative scenarios?
Yeah, so it's known in some systems that assessment strategies might change over the course of a contest, so that they might use one strategy earlier on when certain information is or isn't available, and then later they might switch. So one thing we did do that I didn't talk about was also look at duration of the whole contest, as well as the duration of the pre-contact phase and the contact phase. So basically just using duration as another measure of costs. And so in contests that ended during the pre-contact phase, we found that they ended quicker the larger that the opponent was. So there's no effect of the smaller rival size, but only an effect of the larger rival size, which isn't predicted by any of the models I was talking about. It's not one of the predictions. But that might be because larger spiders are just more willing to escalate. And so that trigger to withdraw at the end of the pre-contact phase is made earlier because of the behavior of larger spiders. Whether or not that counts as assessment or not is, I guess, depends on who's talking about it. And then in the contact phase, we didn't find any effects of size on duration. And one potential explanation for that is just because only a limited number of spiders get to that phase. And so you start to lose the power to try and tell the difference between these things.
Yeah. Thank you.
Welcome.
All right, we have somewhat of a dissertation defense question. So the question is from Lao Yao Yu. They ask, what is a meta-analysis? And so I think if you could actually kind of explain it more in the sense of what was the meta-analysis showing that you mentioned at the beginning of your talk, referring to the assessments.
Okay. I'm trying to remember what that paper was about. They basically looked at a bunch of studies where they tested for mutual versus self-assessment appropriately. So they didn't use studies where they didn't use size difference, but where they used absolute fighting ability of the rivals. And I think they just looked at effect sizes of the predictions of mutual assessment versus self-assessment. So whether the larger rival's size, how much the effect that has on the contest versus the smaller rival size. And so I think they did that with 20-something different taxa, and I think they also had a phylogenetic control as well. So they accounted for the phylogenetic differences, and overall found that there was stronger effects of the weaker rival size, and not so much for the opponent. So overall suggesting that animals rely more on self-assessment, that their own size or own fighting ability matters more than the opponents.
Which again kind of shows the self-assessment is somewhat accurate.
Yeah, I mean, it still gives you the same result in the end, I guess.
Yeah, cool.
Okay, I'm going to read the next question from Jonathan Losses. Do spiders acclimate to videos? That is, do their behaviors change the more times they view the videos?
That's a great question. I didn't look at that specifically. We just randomized the order of the videos that we're presented with. And we also, spiders were presented with a video every 2 days. So we had this like 16-day experiment. So every 2 days, each individual would go through a trial, and they'd be fed and rest in between each trial. So certainly if they watch the same video repeatedly, like one after the other, we'd expect that they tire out, or that they start to reduce their response. But yeah, for the experiment that we did, I guess we do have the data, but I just haven't looked at that specifically.
So I'm sorry if I missed this, but I think we've talked about this before, but how do you know that the spiders are actually recognizing the tiny spiders as a possible threat at all, right? Your data also show like they're just not responsive to them. So how do you know that they're actually responding to the tiny ones?
So they do respond sometimes, but it could be that they're so small that they don't recognize them as a conspecific. But in the field, there are, so this species is found with other jumping spiders. So there are jumping spiders that are larger and smaller than them, as well as juveniles that are smaller than them. And so they'll interact with all these other jumping spiders as well. So even if they're not recognizing them as adult males, as potential rivals, it may still be something that's ecologically relevant to them. But yeah, it seems like perhaps they're not recognizing the smallest videos as real rivals.
Yeah, it's actually a really interesting point about the immature males, right? So they're able to tell whether it's immature or mature by the pedipalps, or what do you think these male spiders are cueing into?
It's probably the sclerotization. Like the adult males they're darker, they have thicker forelegs and thicker chelicerae. I did run interactions between all combinations of like males, females, juveniles. So if females or juveniles display aggressively towards a male, males will always respond aggressively, and then females and the juveniles will just run away. So even if you have a small adult male versus a large juvenile, the adult males seem to be dominant more over the juveniles. But then juveniles and females will also use similar displays to the males, where they adopt these hunched postures. The only displays, the courtship displays, are adult male specific, and there are displays that females use when they're not receptive, which are only presented towards adult males. And then with other species, so like Servaea and incana will display adult males, and they'll use the same aggressive displays towards other species of jumping spiders that they encounter as well. If it depends, they might flee, they might attack, or they might display.
Cool. Excellent. Yusan, do you have another question to ask?
Yeah, actually, I think this one is related to the video question as well. So while I'm looking at your videos, what I'm thinking is how do they judge distance in the videos? So maybe this is like maybe a broader question to actual spider interactions as well, like because things that are closer looks bigger. Like how do they judge whether the spider is bigger or is it like the distance is closer? Do you know anything about that?
Yes, well, I know there has been studies of distance perception in jumping spiders, but I don't know if I remember exactly how they do it. But they have 6 eyes, or 6 functional eyes. The largest pair of eyes are the anterior median eyes, so they're the ones in the middle at the front. And they have very high spatial acuity, but they also have a very narrow field of view, and they overlap in their field of view as well. But in order to get an image, like an entire image of something in front of them, they move their retina around inside their head so that they can view things without turning the head. The rest of the eyes, the peripheral eyes, they all seem to be motion detectors. I think one of those pairs also has overlap. I don't remember whether that has been shown to provide them with distance perception or not.
Okay.
I think there was also some structure in their principal eyes that they have something inside their eyes that I think allows them, like shifts something which gives them some depth perception. I can't remember the details. Yeah.
So essentially your video is simulating when the spider is standing at where the monitor is?
Yeah, so when they were recorded, they were like right up against the glass, and then I scaled it to be the size of, yeah. So when the spiders are right up next to it, it should be life size. Yeah.
Okay, thank you.
Excellent. Well, Rowan, I think we've grilled you enough. This was a fantastic presentation. Thank you for starting us off with such an exciting talk and topic. And I'm sure people will ask follow-up questions because this is stuff that people are gonna continue to think about, right? The size assessment. And yeah, so thanks again, and we'll see you all next Thursday for our second seminar of the semester.
Okay, thanks for the invitation.